Okay, YouTube, in my last video I defined what we mean by a rational function. In this video we're going to work on how it is that we can determine the values of any vertical or horizontal asymptotes for these graphs. So you'll notice that right here I've got a big kind of index that will tell you about the horizontal asymptote. I just want to get the vertical asymptote portion out of the way right now. But vertical asymptotes, okay, basically we can say these occur for all x such that the denominator expression is equal to 0. So if there are ever any x values that cause your denominators to be 0, that's how we're going to be able to find the vertical asymptotes of these graphs. And those are pretty simple to find. When it comes to horizontal asymptotes, though, I've got 3 little bullet points we need to memorize here or pay attention to. But essentially we say if the degree of n is less than the degree of d, then the x-axis, or y equals 0, is the horizontal asymptote. So remember that we're talking about some function here where we have a numerator polynomial over a denominator polynomial. And so what we're saying is if the degree of n is less than the degree of d, that means that the degree is bigger on the bottom of this, or we say it's a proper fraction. Then we say that the x-axis is always going to be our horizontal asymptote. So we're going to refer to this as the bottom-heavy situation, bottom-heavy. So if you ever have a degree bigger on the bottom than it is on the top, then we already know that our horizontal asymptote is just going to be on the x-axis, okay, or y equals 0 in this particular case. We say if the degree of n, so the top one's degree, is equal to the degree of d, it's equal to the bottom expression's degree, then we say then the line y equals the ratio of leading coefficients is the horizontal asymptote. So in other words, if the degrees are equal on top and bottom, then what we'll say is the horizontal asymptote is actually equal to y equals LC of n of x, the leading coefficient of n of x, over the leading coefficient of d of x. We'll just use that ratio right there. And then we say if the degree of n is equal or greater than the degree of the denominator, then there are no horizontal asymptotes. So we say this is top heavy. Okay, so we have bottom heavy, top heavy, and we'll refer to this one as balanced in terms of degree on top and bottom. So all I want to do in this video is find the vertical and horizontal asymptotes for these 3 functions that I've listed off here on the right. And I just want to point this out, before we do anything, we need to simplify these expressions if possible. So I notice that in this first case here, we can factor the denominator into x plus 2, x plus 1, which means that our x plus 1's hit the road, and we say that the simplified form of this rational function is 1 over x plus 2. So I'm looking at this and we'd say, well, let's start with the vertical asymptotes since they're pretty simple to find and, by their nature. We'd say set the denominator equal to 0 and solve this. So if we set x plus 2 equal to 0 and solve this, we get x equals negative 2. So this means that we're going to have an undefined spot on our graph at that point, and we say that there is one vertical asymptote on this graph, and it's at x equals negative 2. Now, for the horizontal asymptote, the very first thing we do is we assess the situation with terms of degree. So I noticed that in the first situation here, we say 1 and 2. We could find out that the degree on top is less than the degree on the bottom. Even in the simplified expression, we could technically interpret this as being an x to the 0 over x to the 1. But the bottom line is this. We say that the degree is heavier on bottom than it is on top. So for bottom heavy things, we say automatically y equals 0. Is our horizontal asymptote. We also can write that this is the x-axis, and this will help us graph things in the next video. But I do want to show you this. If we go in and I type in this expression here, we say here's our expression. First thing I want you to notice is that we do indeed have a horizontal asymptote at x equals negative 2. This was the same value that we got when we set a denominator equal to 0. And then the horizontal asymptote, we say what is that y value that our graph is getting really close to as x gets very large to the right. Looks like our y values are getting closer and closer to a y value of 0. And on the left even, we say as we get to really, really small x values, our y values are approaching 0. So we've indeed confirmed these asymptotes for this problem here. So looking at this next function, I don't think that we can factor the top here, 2x squared minus 1, but the bottom is certainly a difference of 2 squares, so we get x plus 2x minus 2. So looking at this now, I'd say, well, since I can't simplify anything, we'll start by talking about the vertical asymptote, or asymptotes. And I notice that if I were to set the denominator expression equal to 0, x plus 2, x minus 2, then we actually get two zeros. We'd say x equals -2 and +2 would be the zeros we get. So this graph, as a matter of fact, is going to have two vertical asymptotes, one at +2 and one at -2. And as far as our horizontal asymptote is concerned, let's compare the size of the degree. So we'd say in this expression over here we have a second degree over a second degree, or the original expression. So this falls under our balanced instance here. And so we would say, well, the horizontal asymptote is still a horizontal line, so it's y equals a number. But we'd say you take the leading coefficient of the top expression, which in this case is this 2 out front, and you divide it by the leading coefficient of the bottom expression, which is 1. So we get 2 over 1, or y equals 2, and I'm going to put a box around this. So going and looking at the graph, this is pretty easy to see. I'll turn this second graph on here. You'll notice that we actually have a vertical asymptote at -2 and +2. But as far as where's our horizontal asymptote, we said y equals 2 over 1 or y equals 2. You could see how if I were to turn on a line y equals 2, out on the sides, when x gets very large or very small, our y values are approaching that height of 2. Okay, and so my last example here, we have an instance where the top degree is bigger than the bottom degree. We need to start by factoring this as a matter of fact as well. So if we factor the top, it looks like they have a greatest common factor of x squared, and we get left with x minus 1. And then the bottom expression, this is also a difference of 2 squares. We have the same same factors as we did in the last problem. So we could say the vertical asymptotes, setting that denominator equal to 0, we're going to say plus or minus 2. We have 2 vertical asymptotes here. And then talking about the horizontal asymptote, for right now, what we want to say is that because the degree is top-heavy on this rational expression, we have a higher degree in the top than the bottom, we say it has no horizontal asymptote, or no HA. Okay, and we can see this when we go look at the graph here. As a matter of fact, we can state that we have some vertical asymptotes here, and also looks like we have no horizontal asymptote. As x goes to the very far to the left and very far to the right, we can see that that drops out. As a matter of fact, I need to fix this expression here. We had x cubed minus x to the second power, and this was an x squared minus 4. I was wondering why we didn't see 2 vertical asymptotes. There we go. So you can see that when x equals -2, we have a graph that goes way down to -infinity right here and approaches positive infinity in terms of its y values. And at +2, the same thing's happening. But we can see that this has no horizontal asymptotes because as x gets very large or very small or goes to the right and left, our y values either go to positive infinity or negative infinity. They don't get closer and closer to one single value. So using this information about how to find the asymptotes, in the next video we're going to start putting these graphs together. Cheers.